Hello and welcome everybody to the Big Tech Day. It's a pleasure to have you, and welcome to everybody who's watching live or would be watching back the recording from bigtechday.com. A little bit about today's exhibitors or people holding the talk. Last week at the 2025 European Rocketry Challenge, BME Suborbitals came away with the 5th place out of the 30 teams participating in this challenge. Also with 2 awards, the team and technical awards, which is a huge thing, given that they also developed their solid motor. So they're going to talk a little bit about their experience at the race, a little bit about the rocket. And also, I would like to say that I had the really cool experience of watching their launch live last year. It took around 4 hours to assemble everything, the rocket, the launch pad, run the tests, put in the payloads. But man, it was awesome. Me and my 10-year-old brother were really, really impressed. Right, so we're going to have 45 minutes of talks, and then if you have any questions after that, please feel free to ask. I will pass around the microphone. Also, if you're watching live, we will be watching the Zoom chat, so feel free to ask your questions over there. So without further ado, let me pass it over to Emma and Botton, the President and Vice President of BME Suborbitals.
Thank you. Welcome, everyone. We are from the BME Suborbitals team. We came from Budapest, Hungary. This is Botton, the Vice President, and I'm Emma, the leader of the team for this past season. Our story started in 2021, where around 20 students at the Technical University of Budapest came together and decided that they want to build rockets between their university studies. So they started as a small group. They started with small rockets, small projects, and over the year, the team has grown to 100 members. Right now, we work in 8 different teams, and we build rockets, we build CubeSat satellites, and we also develop our own solid rocket motor. So our first rocket launched in 2022 March with this small group of people, the founders of our team, and that year they developed their first competition rocket called Airbus 2, and they participated at the European Rocketry Challenge for the first time, where they managed to fly a rocket, which was a huge step for such a young team at the 2022 competition. The next year, we got involved in the CanSat Hungary competition, which is a possibility for high school students to build their own CanSat size satellites, and the 10 best team has the opportunity to fly on one of our rockets at the national finals. We built 7 rockets for this competition at 2023, and since then we are the annual launch provider for this competition, and we are proud to say that it's really growing in Hungary. This year, over 100 teams applied for next year's CanSat, so it's really growing, and it's a really huge opportunity for us to inspire the younger generations of space enthusiasts in Hungary. We also started to build bigger rockets. At that year, we started with Project Prometheus that we finished in 2024, where we had a test launch in Hungary at a military base, and then we competed at the 2024 edition at the European Rocketry Challenge as the only Hungarian team selected that year. And a huge milestone for our team was this year, the 2025 year, where we managed to integrate our self-developed motor for the first time. And we were the first Hungarian team who could integrate their self-developed rocket motor into their self-developed rocket. So we are really proud of that. We launched it on an integrated test launch this summer, and then we brought it to the competition, which was last week, and we just came back from the competition and immediately come here to tell you our experiences. We also have the rocket that flew on the competition. So after this talk, you can check it out, and we also have it at the exhibition.
Okay, thank you. So just as I would like to explain to you our rocket, Aurora, just to get an idea of how these student rockets, these size rockets generally work. So as you can see, our rocket is separated into distinct sections, or bays as we like to call them. So starting from the rear, first we have a propulsion bay, which houses our own solid rocket motor. Above that, we have an airbrake bay, which I'll tell you a bit later about. Then we have the avionics bay, which houses our own electronics that controls all the measurements and actuations on the rocket. Then we have the payload bay, where we carry our payload. This rocket can carry 3 units of CubeSats, which are standard 10 by 10 by 10 centimeter sized satellites. Then above that, we have our recovery bay, which houses our recovery mechanism, which is responsible for the safe recovery of the rocket, which I also tell you about just a little bit later. And then on the top, we have the nose cone of the rocket. So this is like an overview of our mission, of our flight. So basically, the rocket is on the launch pad. Then the rocket motor is ignited, which starts accelerating the rocket along the launch rail. Our launch rail is actually 12 meters long. That's how long it guides the rocket. Then it leaves the rail. In just a few seconds, the motor burns out. Our motor burned out in around 6 seconds, I think, for this flight. So it's a very short time that the motor is burning, but after that, the rocket continues to ascend for many, many more seconds until it reaches its highest point in altitude, our target altitude. This is what we call the apogee of the rocket, the highest point it reaches. And at apogee, the rocket separates. So this is our first stage of the recovery. This means that the nose cone of the rocket is able to separate from the rest of the body, and this way, first a drogue parachute can come out of the tube of the rocket, and this is a smaller parachute that stabilizes the descent to around 100 kilometers per hour. So it continues to descend at this speed, and then at around 450 meters above the ground, we initiate the main parachute deployment, which is a much larger parachute, which results in a much smaller descent rate, and this way the rocket can touch the ground safely. So as I told you, we have these sections, or bays as we call them, and these bays are interconnected with these radix couplers. So the radix stands for radial axial. So these are a pair of mating part joints and connected by 12 screws. And the trick here is that the screws are at an angle compared to the rocket, and this results in a very stiff connection in both radial and axial directions. And also in our radix couplers not only provide mechanical but also electrical connection. So inside our couplers we have USB-C connectors that go with our bus throughout the rocket. So just to talk a little bit about our bays in detail. So as I said, our propulsion bay houses our rocket motor. We also have an aerodynamic part, the tail cone, and the fins, which stabilize the rocket, which stabilize the ascent, so it goes straight upwards. So inside then we have our rocket motor. This is outline of our solid rocket motor. So basically at the rear we have a nozzle, and then inside the tube of the motor there are these propellant grains. So the title, the solid rocket motor, means that the propellant inside the motor is in a solid state. Both the fuel and the oxidizer are in a solid state mixed together. Our motor uses KNSB propellant, which is also called rocket candy. It's one of the one of the most easiest type of propellants, rocket propellants to produce, and one of the most legal ones to produce. So that's why we also use this. So basically how a solid rocket motor works is that you load these propellant grains inside the motors. Inside the motor, you can see we have 6 of them in our motor. Then you put up an igniter, which is an e-match, an electronic match. So with an electronic signal, we can ignite the propellant. Then in just a fraction of a second, the whole propellant, all the grains ignite and start burning. And once you ignite the motor, there's no turning back. So the motor starts producing thrust and accelerates the rocket. So as I told you, above our propulsion bay, we have an air brake. So as we will tell you later in the competition, it is a very important goal to reach your target altitude, your target apogee as precisely as possible. And one of the easiest way to do is with an air brake. So our motor is a bit more powerful than it should be to reach that altitude. And then the air brakes during flight can deploy. There are 4 blades on our air brake system actuated by a servo motor, and these blades can come out of the rocket during the flight, and they are actively controlled, and they will hopefully bring the rocket to our desired precise apogee. Okay, so above our air brake bay, we have the avionics bay, which houses our also self-developed electronics and flight computers. So in our rocket, we have this removable card structure. There's a common backplane, which different kind of cards and subsystems can slide into. And in this rocket, we had 3 different kind of cards. We had one a power supply unit, a flight computer, and a telemetry computer. So this system is responsible for taking many measurements during flight, also for the actuation of the air brakes and the recovery system. And also, as you can see, we have a telemetry computer. We have also a continuous telemetry link with the ground station, providing real-time data for us. Okay, so above the avionics, we have our payload bay, which houses, as I said, CubeSat-sized satellites. In our team, we also have in-house payload development. This year, we developed a 2-unit-sized CubeSat, which contained a biological and an optical experiment. And of course, these satellites are fully self-sufficient, so they have their own power supply and their own onboard computer to take the measurements and log them. So then at the top, one of the most important part of the whole system is the recovery system, which is, as I said, responsible for the safe return of the rocket. So in our system our separation mechanism works using a pneumatic valve, a pneumatic cylinder. This is what actuates the separation of the rocket. So this is what basically pushes out the nose cone of the rocket. So that way the drogue parachute can come out of the parachute tube, which is it's housed in. This separation is actuated by CO2 cartridges. So the pneumatic cylinder is powered by a CO2 cartridge. So at apogee, we pierce this CO2 cartridge with our also self-developed cartridge piercing mechanism, and this is what pushes out the nose cone of the rocket, so that way it can separate. And we also have a different subsystem for our main parachute deployment at 450 meters, which is actuated by a 3-ring release system. Okay, so that's shortly about their rocket.
Thank you for the overview of the rocket. And now let's see what happened with our team in the past years. I would like to start with last year's competition because it was a huge milestone for us. After 2 years, we returned to the competition with our rocket Prometheus, and everything went well. We passed the technical inspection. We also managed to launch our rocket.
Stations go for Team 7B. Flying on EuRoC Rail 2. Rocket is launching in T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. Lift off.
Yeah, so it went up, it separated, we had our drogue chute, everything looked great, but unfortunately, this was the last time that we saw our Prometheus rocket because we had an issue with our GPS. We lost the signal, so we couldn't find our rocket. We tried to recover it for days. We tried everything. We calculated from pictures using the pixels, and also we use observations from different angles, talk to everyone who was at the launch site at that time. We went back after the award ceremony to look one last time for the rocket, but we couldn't recover our Prometheus rocket at last year's competition. So when we went home, we decided that we have to take a step back and define our mission objectives, our goals, and determine the season 2025 goals. At that time, our team was a huge team, so we had 100 people compared to the year before where we worked with 30 people. So we also had to advance in management. So we decided to make a more structured season, starting with defining the concept and then designing the rocket, the whole system. And we also wanted to do an intense test campaign because we have only 1 or 2 flights a year with these rockets. So if we want everything to go well and work as expected, we need to do previous testing during the whole year. So we also settled a test for the summer to test our rocket in flight before the competition, and after that we really focused on the preparations for the competition. Our 4 main goals were to advance in management, to integrate our self-developed motor for the first time, and also to make this 2-stage recovery system work nominally, because we had some recovery issues in the past, so we really wanted this year to be about recovery and test the recovery. And we also plan to test every subsystem before flight. We had many motor concepts from the past year, so the year started with static fire testing of the motor. This was the first bigger size motor of the team, so let's see how the first static fire went. Okay, it works. And yeah, so we exploded with our first motor, and we think it was a necessary failure for us. So we redesigned our motor concept after that, and we made a fail-safe feature to, in case of overpressure, the nozzle is the one who fails, and it's a really necessary safety feature. So let's see the second concept. it worked finally. So this was the first motor that we decided to integrate to one of our rockets. It's actually a subscale version of our big motor, because in Hungary we can only fly to 1 kilometer, so we needed a smaller motor, a stronger motor for the Hungarian test, and this was our subscale. We actually tested it 4 times before flying it, and also vertically, horizontally, and this was the first part of the. Yes, of course. And, yeah. Yes. So we ignite the motor with electric matches. We have an igniter, and we push the button. It sends the signal, and yeah, it ignites. In parallel with the motor test campaign, we finished our rocket design, so the manufacturing phase could start. We are really proud of that. We manufacture all of our composite components in-house at our university. At the composite laboratory, we use different techniques. We use hand lamination, and also we work with prepreg and more advanced composite technologies. The whole airframe is manufactured at the university, and also the aerodynamic elements like the nose cone and the fins. This year was also about recovery. It was the first time where we manufactured our parachutes in-house. We equipped our workshop with some sewing machines, and then we could start manufacturing. We made a series of drogue parachutes, so we can decide for weather condition that we want to use a bigger or a smaller drogue parachute. So if we want to come down a little bit slower or faster. We also did parachute testing. We have the wind tunnel testing opportunity at the university, and we also have to come out with creative ways of testing when it comes to recovery. So let's see our drop test in a not the most usual. Yeah, but it works. So this way we could test our whole system, and we could simulate the conditions of high accelerations, and we do not harm the rocket. We did this test 3 times during the season. So we went there for 3 days to test our mechanisms. We also test our electronics many different ways. We do thermal testing, vibration testing, vacuum chamber testing for our sensors, and of course the most important test of the season, the integrated flight test, had this July at a Hungarian military base, where we could finally integrate the subscale version of our motor. It was a successful test. We got many valuable data from this integrated flight test. The recovery didn't work as expected, so we had to do an intense test campaign for the recovery after the integrated flight test in the summer to be ready for the competition. And we also developed the full-scale version of the motor, the one that flew in the competition. Yes. We changed the igniters after this slow start to reach a faster ignition for the rocket on the rail. No, it's slow motion. Yeah. And after finishing all of our tests, we the only thing left is the preparation for the competition. We assembled our rocket and presented it for all of our partners at our university. So everyone could see our whole year of hard work, failures, testing, and the result of that dedication and work that the whole team put into this rocket before the competition. And let's see how this year's competition went.
Yes.
Yeah, let's start with that.
Yes, let's start with that. So I will explain a bit about the competition and our experience in this year's EuRoC competition. So basically, EuRoC, the European Rocketry Challenge, is a competition organized mainly by the Portuguese Space Agency and also the European Space Agency each year in Portugal. So this year, this was the 6th edition, so since 2020 they are organizing this every year. So basically this is a competition for student rocketry teams just like ourselves. We have each year around 25 student teams from all around Europe, from great big universities with their own, who bring their own self-developed rocket for this competition. So here's a short list of the awards. So I'd like to tell you a bit about the scoring of the competition. So basically there are 4 main scoring categories at this competition. Firstly, you have the vehicle design, which scores your engineering designs, your engineering excellence, so how good of a rocket you have built. There's a separate category, scoring category, for the technical documentation, so how well you have documented your rocket. You have to submit a technical documentation for the competition. The biggest category, scoring category, is the flight performance. So this scores 2 things. Basically, one is how well, how precisely you have reached your target apogee. And at this competition, there are 2 categories. There is the 3,000 meters and the 9,000 meters category. So you receive points based on how precisely you have achieved this target apogee. And then this category also includes the state of which your rocket came down, so your recovery, how much is it still in one piece, if it could be reused theoretically. So this is the biggest part. And then also there's a 4th category called the team effort, which basically scores your team as a whole, your sportsmanship, your reliability, how well you work together as a team. For all of these categories, there are 4 awards for the highest scores. So the design award, the technical award, there are flight awards for the separate categories, and also the team award. There's a separate payload award, which is given to the best payload, and finally there's the EuRoC award, which is given to the team with the highest overall score, so who placed first in the sum of all categories. So at this competition in Portugal, so basically the competition is 6 days long, and it runs parallelly in 2 different locations. So first we have the paddock, which you can imagine as kind of like an expo, where every team that is there gets their own little booth where they can present their rockets, and this is where everyone can speak with each other, network with each other, talk about rockets, and build a community. And this is where also one of the most important milestones of the competition takes place, which is called the Flight Readiness Review. So at this Flight Readiness Review, basically a board of judges come to your rocket, examine your rocket, ask many questions about your rocket and try to make sure that your rocket is compliant to the rules of the competition and that it is safe to fly. So this year we had our flight readiness review on the first available day. We completed it with no problems, no action items that we needed, so it was all green. I think it was around 2 or 3 hours long, but it went smoothly. So we were really proud of that. And completing your flight readiness review means that you are authorized to go to the launch site on the next day and launch your rocket. So the launch site is a huge military camp, a military shooting range there in Portugal. This is where all the launches of the rockets take place. So basically, you arrive early in the morning, as soon as you can. You assemble your rocket, your final preparations. You do your final tests that you need. There's a last step called the launch readiness review, where also a few judges just take a last look at your rocket to make sure that everything is in order and it's safe to fly. And if you pass the launch readiness review, you are authorized to go to the launch rail, bring your rocket to the launch rail, put it on, put up the launch rail. We put in the igniter of the motor. We arm the electronics, arm the igniter, then vacate the launch rail, go to the spectators area, which is like around 500 meters from the launch rails. And then if everything goes all right, then you are authorized and ready to launch your rocket. So this year we were able to, so we completed our flight readiness review on the first available day, so we were able to go on the first available day to also launch our rocket. So as I said, the competition is 6 days long, and out of those 6 days, 4 days are launch days where teams can go and launch their rockets. So we were able to go on the first day, and we were able to launch a rocket on the first available window. So we became this year's first team to launch at this competition, which was a really great feeling. So let's take a look at our launch.
They are saying that they are ready.
10,
Let's
9,
listen.
8, 7, 6, 5, 4, 3, 2, 1, ignition. We have ignition. Lift off.
So as you can see, we had a great launch. The rocket went pretty smoothly. The motor worked well, the rocket worked well. So actually we went up to an altitude of 2.2 kilometers, which is less than our target, which was 3, but it's not really a big problem. We were really proud to have working onboard cameras, so we have some onboard footage of our flight. So, and just a moment it reaches the apogee, and we will also see the separation and maybe the drogue parachute also. Yeah. So we had a successful separation. The drogue chute came out successfully. So this is the rocket ascending at around 100 kilometers per hour. And we also have a camera view from inside the rocket, which shows the deployment of the parachutes and the rigging system. So this is after the apogee. Parts of it slow down, so you can see it. And if you observe this video, you can maybe see that the lines are a bit tangled onto each other. This was not planned, as you can see right here. So we had this little problem with the lines tangling. So unfortunately, our main parachute did not deploy correctly at the desired altitude. It did not deploy at all. So it came down to the ground at this 100 kilometers per hour of a speed, which is not what it's designed for. But overall, I think that the rocket is in a pretty good condition. So this is the rocket that you can see here that flew. As you can see, we have some damage on the bottom part, which is first touchdown. We have one fin that broke down, but other than that, the rocket is, in one piece. And other than a few internal parts shifted around, but overall, it's in a really great condition. So after you recover your rocket, there's the last review, the post-flight review, where once again a few judges take a look at your rocket, the condition which it came down, and this is where they score, the flight performance, the recovery performance of your rocket. So they take a look at how much it could be reused. So this rocket was deemed unrepairable, which we do not fully agree on, but anyways, yes, so this is our last review. This also went smoothly. So then, on the last day of the competition, we have the award ceremony where they give out the awards. So this year we were so we pretty much achieved our greatest success as a team so far in this year's competition. So as you can see, we have won 2 awards. We have won the technical award for the best technical documentation, and we have also won the team award for being the most reliable team and most efficient team in their operations. And as it was already said, we have placed overall 5th place in the whole competition, which is like far our greatest success so far. So we are really proud of how far we've come from, just this small team from 2021. Now we're here at the first, among the first, the top 10, top 5 among the greatest, universities of Europe. Okay, so thank you very much. This was our presentation. So thanks for the clap. And now we are ready for some questions, I think.
Yeah. So thank you so much for the presentation. Just before we go to the questions, I would like to point out this beautiful logo on the rocket. We are very proud to contribute and be a sponsor to the team. If you have any questions, I'll be running around with the microphone.
So first of all, Köszönöm for the presentation, and thank you very much. Vielen Dank. Congratulations to 5th place. And
thank you.
I have one little bit of an evil question. You were 5th place, but the rocket hit the ground at 100 kilometers. At what speed did the rockets of the 20th place hit the ground? What did they look like after it was all said and done?
So, there are always some interesting rockets each year. There were some that pretty much blew up during the flight. But so the state that your rocket comes down is, just one scoring category. So that is not what only determines your overall place. So, we got low points in that category, but overall we got higher scores from the other categories. So that's why we were able to be placed 5th.
Thank you very much. How did you scale the motor? Because basically you cannot just linearly scale the motor when you build the bigger one. How did you do it? Like, was it exponential? Was it quadruple?
We have this open motor that can simulate the motor. Basically, we calculate all of our solid motors with that. So we designed using this one and also other calculations and simulation, the first subscale version. Then we tested it, and from the measurement data, the open motor and other aspects, they scaled it up. It's the hardware is basically the same, only the casing is longer, so it can house more propellant, but it's not a linear. So it's not a linear connection between these two motors, and then we also tested and measured the bigger one. So that's how we validated our design.
Right, and where did you get the recipe from?
If you type in KNSB into Google, you can find the recipe.
Yeah.
So my question is for the future. So do you plan to repair the unrepairable rocket and fly it next year to rub it in their face?
Not really. So it goes to the wall at the workshop, and we're starting with new projects for the next year.
All right, I have many questions, but I'll restrict myself. So it looks like you have quite a lot of acceleration right at the start. So what's the peak acceleration you hit? And did you try like slow acceleration and longer burns?
So I think for this flight, our peak acceleration was around 5 Gs, which is, I mean, it's still not a lot compared to a few other rockets. So there are definitely higher Gs than that. So basically, about your last question, there's a rule for the competition that the point at that the rocket leaves the launch rail, so it's fully, free to move. So it's not guided anymore by the launch rail. It has to be at a speed of 30 meters per second. So that's why it's a stable flight. If it comes really slow down the launch rail, then it can pretty easily tumble. The wind can tumble it, and it can go into a direction which is not desired. So that's why we pretty much need this acceleration. So it's required by the competition. Yeah.
Great, thanks. And maybe one more. I saw that you have some sponsors. What's kind of the overall financing? How does it work for a project like this, if I may ask?
We always get this question, but we cannot really calculate the whole value because some sponsors give us the opportunity that they manufacture our parts. For example, this radial axial coupler, some sponsors gave us materials, some sponsors gave us money. So the whole year's finance is just we never had the chance and the time to actually summarize, and we don't need that for the competition. Like in Formula Student, you need to calculate your costs, but it's not the case with our competition, so we focus on other management aspects, not calculating the price of the whole rocket.
Yes, but as you can see, we have many sponsors. They are all presented, listed on the rocket. And yes, as Emma said, they are very different kinds of sponsors, some who manufacture, some who provide some service to us, some who give materials and so on. And of course, softwares, and of course, some who provide financial support.
As a little bit more technical question, when you showed them card modules for essentially the avionics bay,
yes.
The power supply unit, does it really come with an integrated battery, and that's the thing that provides the power through the whole bus?
No, so that we have the battery was not presented. There's a separate place for the batteries. So we had Okay. This was not presented the batteries, so the power supply unit is only responsible for producing the bus voltages. So we have 12 volts that goes throughout the rocket, and we have 5 volts that is mainly used inside the avionics bay for the other cards. Yes. Yes, it's a pretty beefy PCB. Yes.
Yeah, that's what I was wondering. So, like, where does the power come from? Thank you.
Yeah, one question about the velocity. So you said the rocket came down in the end at around 100 kph. What are the velocities at start after the max G or max Q? And like from the pictures you showed earlier, it seems like you have an acceleration that's very short, and then most of the time the rocket is actually coasting, right? So could you tell more about that?
Yes. So actually, the motor only burns like for 5 or 6 seconds. So that's the only part where you have acceleration, and from that point the rocket is coasting, so deaccelerating. So for the numbers, so as I said, we have around 5G peak of acceleration at the start. Then we have around 30 meters per second when the rocket leaves the launch rail, which is around 100 kilometers per hour. Our peak speed, I think it was around 230 kilometers per hour. So it's it's a subsonic rocket, so it doesn't reach the sound speed. Yeah, so that was around our max velocity. And yes, with the drogue parachute, we have also 100 kilometers per hour, and with the main parachute, there should have been around 15 kilometers per hour for descent speed.
Yeah, congratulations, and thank you very much for the talk. My question is about efficiency, weight efficiency in particular. Can you comment on the ratio of payload to overall weight and fuel to overall weight?
So we had 2.5 kilograms of payload in this rocket, because we also had a CanSat from the Hungarian national finals. Our fuel is around 10 kilograms, and the overall rocket is 40 kilograms. So it's a heavy rocket, for a quite heavy rocket for this motor and for this 3 kilometers. And for next year, we definitely want to lose some weight from it, because this year it was a new concept, so we tried out new things, and the focus wasn't on weight efficiency. And for next year, it will be definitely a goal to reach higher altitudes with this rocket.
Do you have any plans to tackle the 9,000 meter challenge? And regardless of whether you do, would that just take a bigger engine or a bigger rocket, or would the rocket need to be multi-stage at that point? What would that take?
There are many possibilities. With this rocket, we have to definitely lose some weight and put a stronger motor with it. We didn't plan it for 9K, so maybe with a different rocket. We also want to use different propellants that are more efficient, but it's really hard to get those materials that are legal in Hungary. So that's why we use the KNSB propellant this year. So with this KNSB, we couldn't reach, I think, the 9K, but with a different rocket, we could. We don't need to go multi-stage.
Yeah. So, and just as a comment, so what we didn't really tell you about that at this competition, there are 3 kinds of propulsion technologies. So we have the solid rocket motor that we talked about, and there are also hybrid and liquid motors. So in our solid, the propellant and the fuel and the oxidizer are in solid state form. So in a hybrid rocket, the oxidizer in a liquid form and the fuel is in still a solid state form. And for a liquid rocket, also called like a biliquid rocket, so both the fuel and the oxidizer are in liquid form and are pressurized. So so maybe tackling the 9K would be easier with a different kind of motor at this size, yes, which is we're really not sure which direction we will go next year, but yeah, these are really exciting directions, yeah.
Bit of a silly question, but how do you transport the rocket from Hungary to Portugal?
We rented a van and put together all of our equipment from our workshop to be able to assemble or even to fix our rocket, and also the rocket and the propellant, and 3 amazing drivers drove across Europe. It's like 3,000 kilometers drive from Budapest to the competition, and another 3,000 to come back. It's a 2-day trip for them, so we really appreciate that they did it for the team. I think at this point we couldn't manage it with an airplane. Some teams do that. So, for example, there's a team from the north of Norway, and they packed everything into suitcases, and they transported their rocket as a luggage on the plane.
Right, a question from Zoom then. You mentioned that you recently ramped up from 30 to 100 people in the team. And what strategy did you use to manage this big team effectively?
It was a challenging year to figure this one out. We put more people into leader positions to put out some weight from the sub-team leads. So, for example, in the structures team, they work on the airframe, but they also design these metallic couplers and also the internal structure of the rocket. So they have a lot of work, and we had 2 leads for that sub-team. But for this year, where we want to start with a new project, maybe we need another strategy, because it worked out, but it's not the best.
So thank you for your presentation, and congratulations to your achievement in the competition. I have a question about the altitude. So the point that you reached was, I guess, 2.2 kilometers. And how do you already have some indication why it was not 3? Or do you go into the competition expecting to reach 3? Or do you say, yeah, 2 is fine and everything beyond that is bonus? Or what's your expectation, and do you have some indication to the result already?
So yes, so we basically went into competition knowing that we will most probably not reach 3K. So this is mainly due to the rocket being more heavy than we initially planned it and designed it, and also the motor being a bit more underpowered than we expected. But actually, based on simulations, we did expect more than 2.2. We expected around 2.67, yes. And just to answer your question, we do not know yet why we did not reach that height. So basically, it's really hard to get any idea of why it flew like that. The motor could have been a bit less powerful for this batch of propellants, or there could have been some more heavier winds than it was predicted at the time. So basically we don't know, and it's really hard to know. So yes, but we'll try to figure it out.
Right, thank you. Unfortunately, we have run out of time. I know there's a lot more questions. I see the hands. Thankfully, the guys are going to display their rocket in the shifting station in the big building. So if you do have any more questions, you can find the guys over there. And thank you for the presentation. It's really interesting.
Thank you.